Okay, so this is the 2023 paper, and for this paper, I'll be going a bit faster because yesterday's video was 20 minutes long. So for question 1, part A, it asks us to draw the Lewis structure for the SO4. So we should already know how to draw this from yesterday's video, we already covered like most of it. First thing would be to identify the electrons of each atom inside the molecule. So it's 6 for sulfur, 6 for oxygen, and 7 for fluoride. But since there's 4 fluorides, we have to times 4. Total will be 40 electrons. Then you draw the resonance structure and you realize that actually the second one is the most sound one. I mean the most possible one because the formal charges are the lowest. For the second part of this question, we're asked to find the hybridization of the central atom, which is sulfur. So from the resonance structure, you realize there's actually 5 electron groups, 4 single bond and 1 double bond. But you have to keep in mind that a double bond still counts as 1 electron group. And from this, you can deduce that it's sp3d hybridization. Yeah. The second part of this question, we're asked to find whether the molecule is polar, and it is polar because it is asymmetrical in shape. For the next part of this question, we are asked to find the theoretical bond angle by Vesper. And the best way to do this would be through electron geometry. So by drawing out the diagram, you realize that it is trigonal bipyramidal. That means that the angle would be 180 along the vertical plane, and between the atoms on the equatorial axis would be 120. So that is the theoretical bond angle, but the actual bond angle will differ because of the oxygen double bond. The oxygen double bond means there's greater electron density that will push the two fluoride in the vertical axis away from it, which is why you have a bond angle of greater than 90 degrees. Question 1 part B asks us to draw the Lewis structure for these two molecules, BCl3 and NCl3. So using the same method, you can draw it easily. And for BCl3, the electron geometry and molecular geometry is the same. But for NCl3, it is tetrahedral and trigonal pyramidal. For NCl3, it's polar because it is an asymmetrical shape. So for part C of this question, we're asked to draw the Lewis structure and then predict the hybridization. And using the same method, we can get it. So this should be pretty straightforward. Okay, so for the last part of this question, part D, we're asked to find what are the possible elements for E. And we do this through formal charges. So first you have to note that the charge of the atom is 2 minus. Then you find the formal charge of fluorine and oxygen. For fluorine is 0, and for oxygen it's -1. So by balancing the equation, we get the formal charge of E, which will be -1. So the next thing to do after finding the formal charge would be to find how many electrons E has, like how many lone pair electrons and how many bonding pair electrons. So there's 4 lone pair electrons and 3 bonds. Then we'll use the formula for finding formal charge to get which group E can be. So -1 would equal to X, -4 -3. So X would have to be equal to 6. So X must have 6 valence electrons for this equation to work. And hence it will be group 6. So after identifying that it's group 6, you have to see that E actually has more than 8 electrons. That means it has expanded its octet, which will indicate that it will be period 3 and below. Hence it will be sulfur, selenium, and beryllium, or whatever that thing is. Okay, on to MO diagram. So I think the first thing you need to do for MO diagram is to identify whether there'll be sp mixing. And for homonuclear molecules, it would be quite easy, but for hetero molecules, it's a bit more difficult. But the notes did list that CO and NO mix, so I think that is something that you need to memorize. Alright, so after you draw an MO diagram, it should look something like that. So just bear with me because it's a bit messy, but the thing that you have to take note is that the oxygen orbital is actually lower in energy than your nitrogen, which I did draw a bit of a difference there. Yeah. Then after that, after drawing everything, you will be able to find the paramagnetic. So NO and NO minus would be paramagnetic because they are unpaired electrons. And after that, you find the bond order. So keep in mind that the higher bond order would mean that it's the shortest bond, which is why NO plus would be the shortest. Part B of this question asks us to draw the lithium hydride. So they already give us a hint that the 2s orbital of the lithium will bond with the 1s orbital. So if you draw, it will look something like that. And the 1s orbital of the lithium would be non-bonding. That's why I drew it there. So for this one, the lithium is actually higher in energy than the hydrogen. So that's why the orbital is a bit higher. Okay, so on to the NMR question. So for this question, I'll be spending a bit more time on it because I feel like it is more challenging than the other question. And we're given like two compounds and then given an NMR spectrum and to identify which one is the correct one. So for the first thing you want to do is to identify how many signals you have. So you can see there you have 4 signals. And when you have 4 signals, the first thing to do will be identify how many signals you will get from your compound. So sometimes you might be able to eliminate it straight away. But in this case, both of it has 4 signals, which is kind of sad lah. Alright, so the next thing you have to do will be to identify the multiplicity of each signal. So the first signal will be a singlet, second will be a triplet, the third will be another singlet, and the fourth would be a quartet. And from the use of this singlet, right, you can actually identify which is the right one already. Okay, so let's look at compound A first. So the H at the one position, right, is CH3, and at the second position is CH2. So these two will couple to each other. So at number 3 is the CH2, and number 4 is the CH3. And these two will couple to each other. So actually, you already identified which compound is correct, because compound A is definitely wrong, because there will be no singlet from it. Okay, so to double check, we'll compare the singlet signal to compound B. So the first signal will actually correspond to the cross-section area of the compound B. Okay, so let me draw out how it looks like. So a single central carbon will be connected to 3 other carbons, and each of these carbons will then be connected to another 3 hydrogen. And all of these hydrogens cannot couple together because, okay, let me draw it for you. Because it's actually 4 bonds away. So we know that only 1 to 3 bonds away can you couple, but if it's 4 bonds, you cannot couple. That's why all of these hydrogens will produce one signal only. Okay, so to triple check your work, let's look at the hydrogen at the third position. So let me draw this hydrogen out for you. This hydrogen is actually a lone hydrogen. It doesn't couple to anything. And because it is in between that 2 oxygen on the left and right side, it's actually quite distributed, which will correspond with that singlet near the 3 ppm area. Alright, so after you label all your magnetically equivalent protons, it's time to draw your label tree diagram. So the first is A. A couples to B, and B is a CH2. So using the M+1 rule, you have 3 signals. And you do the same thing for B, you will get 4 signals. From just now, we already know that D doesn't couple to anything, and so does C. So they both have 1 signal. And really deduce that actually C will be the most shielded one. So from just now, so you already know the answer for the last part. Yeah. Okay, so the next part of the question asks us to find coupling constant. And we can find it by using the operating frequency multiplied by the space in between the signals. So I've gone ahead and done it already, but you see that 300 is given in the question, which is the operating frequency, and the 381 over 20,000, this just your signal 2 minus signal 1, yeah, and you get 5.715 hertz. For the second part, since we're given 4 values, we'll have to find the average of this distance between each signal. So you just get the distance, then you divide by 3, since there's 3 spacing in between each of them, and you get 3.573 hertz. Now the answer is if these protons couple to each other, and the answer is no, because the two coupling constants are different, hence there is no coupling. Alright, another NMR question. So we're given the formula C9H12 and we're given 3 signals. So the first thing you want to do for this question would be to identify whether your molecule is saturated with your hydrogen or not. So the formula is actually would be your number of carbons times 2 plus 2, and that's 20. And 20 is not equal to 12. That means you're not saturated. So this will mean that you either have pi bonds or you have a ring. Well, the next thing to do would be to use the information that they've given us. So they told us there's a set of resonant signals centered around 7.25. And the 7.25 should give you a hint of what it is really. So it's actually a ring. And what kind of ring, I have no idea. I don't take organic chem, but it is a ring. So let's draw the ring first. Second information they give us is there's a doublet at 1.25. So if you compare the signal of 1.25, we actually realize it is the most upfield one, which means that it's actually the most shielded region. So it's the furthest away from the ring. And a doublet would indicate that it couples to a H. So most likely it couples to a CH. Okay, next, it told us there's a septet at 2.9. Okay, 2.9 will be further downfield than 1.25. So that means that this hydrogen would be closer to the ring than the first one. So you can really imagine how it looks like. You have the ring, you have the septet, then you have the doublet. And if you think about it, a septet can be caused by two different things. First is a double coupling, like maybe a triplet or triplet can cause a septet, or it can be caused by coupling to two CH3s, since CH3s are magnetically equivalent, so that means it will be 6 plus 1. But because you see there's 3 signals here, it cannot be a double coupling, because a double coupling will give you 4 signals. So we deduce that it's a CH3. So from this, you already know what structure you will get, because you have a CH and you have two CH3s. So basically, just write out. So you have the ring connected to one carbon, connected to a hydrogen, which connected to two CH3s. Yeah. And you can make sure that it couples because you see the number of bonds. It'll be 3 bonds away. Alright, so the last thing you need to do would be to count the number of hydrogen carbons and make sure it tallies with the molecular formula. And in this case, it does, because you have 5 in the ring, 1 in the CH, and 3 in the CH3s. Alright, so for question 3. So part A is actually on entropy, and I don't want to do it because we're not taught, and I'm hoping it doesn't come out. But you can actually do part B without doing how to do part A. So part B asks us to find if the percent yield increase or decrease when raised temperature. And this can be done through a bit of logical thinking. So the standard enthalpy can be calculated through the sum of the formation of products minus the sum of formation of your reactant. And that will indicate that this reaction is actually exothermic because it's negative 197.8 kilojoules. Okay, so let's think about it. When we increase temperature, we actually increase the rate of reaction. But since this reaction has equilibrium, we are increasing the rate of reaction in both directions, not just the forward, but also the backward. Yeah. Alright, because it's an exothermic reaction, if we increase the temperature of the reaction, right, we're actually increasing the energy of the products. And that will actually force the reaction backwards. So instead of getting your products, you'll get back your reactants. And from this, you really can tell like how increasing temperature would affect the percent yield. Because you have more reactants than products, your percent yield will actually decrease. Then you can use this to actually solve part C. Because of your decrease in yield, you'll have more reactants, and more reactants in this case will have more moles, which will increase pressure. Alright, so for question 4, we will have to find the balance equation before we can proceed any further. So the first thing to do would be to balance the equation, which will get 2N2O5 will give you 4NO2 plus O2. Alright, next is to find the amount of moles that reacted. So we know that 2.8 grams reacted. So 2.8 divided by the molar mass, which will be 108.02, will give you the moles of 140 over 5401. Okay, next, using the first order integrated rate law, we can find the concentration of A. Just sub everything in. But don't forget to convert the 15 minute to seconds, because the integrated rate law uses seconds instead of minutes. Alright, so by subbing everything in, you get the concentration of 0.005613. So your initial moles minus your current moles will give you how much has reacted, which is 0.02031. Now, next we have to look at the balanced chemical equation for you to know how much products has formed. So 2 moles will give you 5. So the ratio is 1:2.5. So for every 1 mole, you get 2.5 moles. So 0.02031 has to times 2.5 to get you the number of moles of your products, which is 0.05077. So next, the amount of moles of products formed plus the amount of moles of your reactants left will give you the total amount of moles inside the container. So which is 0.05638. Next, using the ideal gas law, we can find the pressure from this amount of moles. So basically divide both sides by volume and then sub in everything and you get 0.76 atmosphere. Alright, so for part B and part C, I don't think he went through it during the notes or during lecture. So I don't think it'll be tested, but maybe you wanna learn. I don't know. I had to search it online also. So anyways, I don't even know I'm correct because yeah, I have no reference for this. Okay, so the first one you need to find is your rate of reaction, which is your K constant times the concentration of your reactant, which will be 4.4 times 10 to the power negative 5. Then next will be to find the standard enthalpy, which is 110.8. You multiply both together, you get the rate of heat absorption, which is 4.89 joules per second. And this is, I think it's intuitive because enthalpy is the amount of energy released per mole, and for reaction rate is the amount of mole formed per second. So you multiply two together, you will get the amount of heat absorbed per second. I think that makes sense, right? So then for part C, it's just a formula. So N0 is just the amount of moles that you use, and A is the coefficient of the reactant. Then you just sub everything in, and you get 1.01 kilojoules. Yeah.